Are we? Oh,
Yes. Okay, we are live. So hello everyone. Bear with us, I guess, as we kind of figure all of these things out. I can kind of go over just for today. The main speaker will be coming in 10 minutes, but we will be giving kind of a brief intro of what this all is, what you guys can expect for the coming few days. So basically, this series is going to be, as you already know, on this YouTube channel for the next 5 days. The actual starting time is going to be slightly different every day, just to accommodate the speakers. But in general, what we're going to be talking about during this time is roughly like how certain components of these kind of frontier large transformer models have evolved over time. And each of the speakers is going to be talking about one like particular component. And some of these components are relevant to things like GPT-OSS. Some of them are not directly relevant, but they're sort of the architectural or systems level changes that kind of like underpin all of the recent advances in all these different models. And so you'll get a lot of really, really cool talks from authors of a lot of these works. But yeah, so also the three of us are going to be organizing most of this. So I'm Alex, in case you guys don't know, if you guys want to give a little intro.
Oh, I'm Joe. Yeah.
I'm Han.
Yeah, and they're from the ScaleML side. I'm from the GPU mode side. So basically, like what is kind of going to happen throughout this week is you're all probably familiar with the base kind of transformer architecture from the Attention is All You Need paper. And a lot of you are probably also familiar with some of the kind of newer architectures. And so what we're interested in exploring this week is kind of like what has changed in the past like 8 or so years. Especially from these like original kind of decoder only models, like what sort of components have been replaced and what sort of components have evolved over time. And so to give kind of like a brief overview of what's going to happen. So today we're mostly going to be talking about MoEs. There's going to be some other stuff in the context of FlexOlmo, but basically like looking at the feed-forward layer and how this has been kind of replaced with MoEs for larger models. Tomorrow, we're going to be talking about attention sinks and other stuff that are kind of related by one of the main authors of the paper. The day after is going to be about quantization, mostly in the context of these like large models. So it'll cover things like MXFP4 and some of the like newer kind of data types that are being used for training and inference. Thursday will be by Songlin on positional encodings and also path attention and some other works that she's been exploring. And then finally, the last day is going to be everything related to GPU programming, accelerator programming, and things of this nature. So we actually will have 2 speakers that day. And this is like the full schedule. So all of these very, very wonderful speakers will be giving roughly hour to hour and a half long talks on topics that they are experts in or that they themselves kind of founded. And so I think this is going to be a super, super exciting time. And I hope you all enjoy. And the other thing, by the way, is that you can ask, if you're not familiar with this like GPU mode format, you can ask whatever questions you want in the chat. And during certain times in the middle of like a specific speaker's talk, we will basically ask your questions for you. We'll put them up on the screen, stuff like this. And if you have any follow-ups, you can just continue to ask the chat. And feel free also to answer questions as well in the chat if you know, and we will try our best to as well. So yeah, I'll leave the rest to Joe.
Yeah. So we're going to talk about mixture of experts today. And mixture of experts have been one key dimension in which models, or one key technique that have enabled models to scale. You can go to the next slide. And if you think about it, we know more parameters are nice. But the thing is that it's also expensive in terms of flops, right? And you can think, if my model is like training on so many different tasks, right? These foundation models are really like true multitask learners. For a specific input, do we really need to utilize all the parameters? And that's kind of the perspective that MoEs take, which is we can just use a subset of the model's parameters per input. Intuitively, you can think about it as, what if these experts have like different specializations? Although they're in practice, they don't have like a clear semantic cut of specializations. It just allows you to grow your model size, but not have to pay as much of the flops as if you had like a dense model activating all the parameters. So as you know, in like the GPT-OSS model, there are two versions, the bigger one, the smaller ones. And in the bigger one, that's like around 120 billion parameters, only 5 billion are active. And similarly, like in the small one, only like 3 are active. 3 billion parameters are active. Go to the next slide. Wait, this was the older slides.
What do you infer? I think Joey already have a question in the comments.
Sorry, I was muted. I didn't realize. Yeah, they can't nerf me asks, don't you pay all of the flops at training time though?
Don't you pay all the flops at training time though? Well, even in training time, each token, if it's routed to like a subset of experts, it's not routed to all the experts, right? So you do also save some compute there. We can go one slide bit back. Yeah, and so yeah, you can just see in this picture here that in the GPT-OSS model, what happens is every token is going to be routed to a subset of 4 experts, right? So in the large model, there's a total of 128 experts, and every token is individually going to route to 4 experts. And just to be clear, these experts are actually the MLPs of the original transformer. So in the original transformers, we had the self-attention, then MLP layer in one block. And what happens now is, instead of just having one MLP, we're going to treat the MLP as experts and create many of them, many separate MLPs, and then every token is going to go to 4 of them. So if we go to the next slide, what I did here for like educational reasons is I took the actual code from GPT-OSS, and I'm just going to step through just the MLP block of the code, and specifically the forward pass, and we're going to just go through it line by line, just so that we have a good primer before Sewon presents her talk. So pretty standard, we have our tokens X coming in. For now, let's just, for pedantic reasons, we're just going to treat it as one individual token has a hidden dimension of H. We're going to do the RMS norm. Now, what we're going to do is we are going to, it's a small typo, it should be WT, but anyway, so we're going to project this token to a space that has the number of experts, like a linear projection. And this is going to give us like our, after softmax, top K and software, we're going to get the like, this is going to tell us which experts are we going to pick. So specifically in the GPT-OSS, G is going to be, if we take the large model, like a dimension of 128, we're going to now pick our top 4. In the illustrated reasons, I just drew 2. We're going to take the 2 largest ones, which is indicating the model is saying these are 2 best experts for this particular token. So we're going to get the indices of these experts, so we know which of the MLPs we're going to choose. And after normalization, we'll also have their respective weighting. So now we have, for the token, we now know which experts we're going to pick. We also know how much we're going to weight their experts' outputs by. So we can go to the next slide. So now this is kind of like more of the meat of the MoE. The router is quite a lightweight layer, but the MoEs actually take up like around 90% of the MLPs take up the majority of the parameters of a transformer. And because of this, we're going to actually use tensor parallelism. So what I drew here is, just imagine we have two GPUs. So our normalized token T is going to come in, and the forward pass is going to be running on each GPU in parallel. So I'm just drawing this all in a parallel view, but like our token T comes in and it's sent to our respective experts. We picked expert 3 and 5 based on the top K routing previously. So our token's sent to these two MLPs. And the code I've highlighted on the left side. So like I've color coded the code with the corresponding section in the figure, green, red, purple, blue. So the green part is we're actually going to just do the normal MLP computation. So linear projection, Swiglu, another linear projection. Now, for this part, I want to touch upon briefly the tensor parallelism. So if we look at just, for example, just the first projection of the MLP, in the box above, in the top left, I have described how, well, this is in the code, how it's defined. And you can see that it's for every expert, it's actually just going to shard up on the output side. So each device is containing all of our experts, but only a piece of the matrix, like of the projection matrix. So what we need to do is we're going to pass our input through all the devices. They're all going to each use this sharded matrix and multiply it by our token. And at the end, it's going to like gather and sum all of them as if it's doing like one normal matrix vector multiplication on the full matrix. So yeah, the green part is each device is going to do a sharded multiplication. And then at the end, after our device has done this, we're going to do it all reduced. So the devices are going to communicate, and we're now going to sum, and each device is now going to have the same copy, like our tensor T afterwards went to expert 3 and 5. So now we have these two outputs coming from our two experts. And again, just to reiterate, it's going to be the same values on all the devices. And finally, we're going to just multiply them by our expert weights, which is like highlighted in purple. So we're going to do this weighted sum, which is just saying how much to weight each expert. And then finally, we're going to add the residual connection, add our original token X back in. So this is just like kind of giving you the overlay of how it's implemented in GPT-OSS. It's like quite a standard implementation, top K routing. Now, some important details that are not included in the code are actually the load balancing function. So one of the biggest issues when training these MoE models is actually the router collapsing all. So you can imagine, ideally we want for like a whole diverse variety of inputs, we should be using different experts, right? Under the notion that, these experts are having like some specialization. It would not make sense if we're sending all of the tokens just to like a tiny subset of experts. That's kind of like defeating the purpose. But during training, the router is randomly initialized, the experts are randomly initialized. There's no incentive for the model to spread its tokens across. And that's why we have these auxiliary loss functions added, such as load balancing, which are intuitively, there's many variants of these, but intuitively, they're just trying to make sure tokens are getting spread across experts. And I see there's a question. Could you say more about comms versus computational trade-off? Han, do you want to talk about this? I think Han is
Yeah, so I'm looking at the question. Can you say more about communication versus computation trade-off for tensor parallelism? So I think for tensor parallelism, I'm speaking of in general. So for general, tensor parallelism has our tensor parallelism are designed for reducing the latency. The price you pay is you pay for the extra communications. So as a result, for inference, usually people use a lot of tensor parallelism to reduce the latency. But the price you pay is you pay because tensor parallelism, especially doing the passes for the model, you actually had to do a lot of communications between different layers. So if you're in a community network bound cases, actually tensor parallelism is usually not recommended because you actually pay a lot of prices for doing this. But if you care about just making the time for second extremely fast, that's really the way to go. In the cases when you have network bound and you care about throughput, for example, then sometimes in some cases there's a lot of factors regarding the actual infra setup. There's actually cases you might need to prefer a different type of parallelism based on the specific cases.
Nice. Okay, so we can, I think we can move on to the next slide. This is coming more, stepping back from just like the very fine-grained details we just talked about, which is in a lot of these existing MoE models, there's a fixed number of experts. And it's almost like a hyperparameter. You just fix them, you train them, and it's static in the sense that you can't add experts continually, right? And for the purposes of just like, if you just want to train one model and you just want to use it on inference time as is and not change it, this is great. But I think the whole point of like MoEs is kind of, we want to start making our models efficient and also like dynamic in the sense that it's intelligently routing to the right subset. But utilizing a lot of this machinery, we can think about what about experts could actually be introduced dynamically? Like, what if you and I, like, let's say Han trains an expert, I train an expert, Alex trains an expert. Each just now has also like a very clear semantic skill. How do we now create a model that's able to allow us to pool our experts together, right? I think there's a lot of capabilities you can gain when we can treat our model as more dynamic and people can continually add experts that have specializations, and it comes into more of this idea of decentralized training, which Sewon's talk is going to talk in full-fledged about. But this is just kind of setting the stage for Sewon's talk, and who unfortunately is going to be there in like around 7 minutes. There was a fire in her building, and she's driving to her home now.
Actually,
so yeah,
she is here.
she's here.
I think so. It said she.
Oh, okay,
joined.
okay.
I can't find her on the thing. But actually, while we're waiting, Ashish had a question. Can you talk about shared versus non-shared experts and their trade-offs?
Okay, I can't talk in too detail about this, but a shared expert in the high level is when you're going to have some common, I believe it's when you have like a common set of experts. Because like in the original top K routing, you could be choosing completely different subsets of the 4 for every token, right? If you're doing K equals 4. But some people have experimented with like, oh, what if you actually have some fixed MLPs, like this MLP will be always routed to, and some can be selected with top K. That's what I believe it is. I don't know too much about their trade-offs versus non-trade-offs, but yeah, hopefully that answered something. Yeah. Okay, and Sewon is here.
Okay, yeah, let me try to share the screen.
Yes.
Yeah, hi everyone, and I'm sorry for being late. We had an emergency fire alarm in my office for some reason, so I just came back home for a presentation. So just to introduce myself, I'm Sewon. I'm an assistant professor at UC Berkeley ECS, as well as research scientist at AI2. And today I'm very excited to present our work, which is about mixture of experts, but for addressing a different problem on training on distributed data sets. And actually, I cannot see people when I'm sharing the screen. So if you have any questions or want to raise anything, please let me know. Please just speak out so that I can hear. And also, I would like this to be interactive. So if you have any questions, please just feel free to interrupt me. Cool, so I'll get started. And before I get started, I'd like to mention my co-authors, Weijia, Akshita, and Kevin, as well as other collaborators who have made all of this possible. So what is this talk about? So I believe in the previous slide you learned about standard mix of experts, where the key idea is to activate a few parameters instead of all parameters for training efficiency as well as inference efficiency. But mixture of experts also have other benefits, like it naturally provides modular architecture. So the question we want to ask is, beyond efficiency, what are other benefits we can get from this modular architecture? And in this talk, I'll present our particular work called FlexOlmo, where we use mixture of experts to enable training on distributed data sets owned by different parties. And different parties do not want to share the raw data, so it's very difficult to pull all the data together and train one model. But we'll tell you that because mixture of experts naturally have modular architecture, it's possible that different parties train different parts of the model and they can be merged into a single model. So in the rest of the talk, I'll first clearly define the problem setup and convince you why this is an important problem to solve. I'll also talk about what are the alternative approaches, either not using mixture of experts or using mixture of experts. And I'll also talk about what challenges there are in those approaches. And then we'll talk about our method, which is using mixture of experts. And we'll tell you how we are addressing the challenges that I mentioned previous approaches have. And then, of course, I'll tell you about the experiments and the results we get compared to the model without any distributed training like this, and also compared to the upper bound model that is trained jointly on all data sets altogether. Cool, so let me get started from the problem setup. So in standard language model training, we typically assume we have centralized access to all data throughout training. So model developers should have access to all the training data and train one giant model all on this data. And of course, here we assume that data access is binary, either available or not available. And we take this as granted. And if we hear about it, it sounds very obvious. But I want to argue that these two conditions may not be optimal in practical scenarios. For instance, in reality, data access may not be binary. It is rather a spectrum. There could be data that model developers may not have direct access to the data, although they can potentially use the data. Or there could be restrictions, like data should be stored in a very specific location, like GCP or AWS, and cannot be transferred, in which case pulling all the data together and training one giant model is very difficult. And these are some of the examples of restrictions. There are more restrictions in practice. For instance, data may be available at different times. You may have to opt out some data later on, or you may have new data coming in later on so that you want to incorporate them. And you want to do all of this without needing to retrain the whole model from scratch, because that will be very costly. So what we want to do is to propose a model that can support modular distributed training. And here is the exact problem setup. First, we assume we have some starter model that is a shared model trained on public data only. So this is the data someone could pull all together and then train one giant model on that. And then we have a set of data owners who didn't release their data publicly. They want to keep their data local. but then they take the shared model and then do training on their data independently from each other. So here, the boxes here means this training is completely local and independent. You don't even need to share the data, and this training can happen asynchronously across different data owners. Once you do that, then what we want to do is to have a combined model by combining model trained by different data owners as well as the shared model that we use as a starter model, and have a single unified model. So this is kind of like a collaborative training setup where different data owners are collaborating to make a single model, but without needing to share the raw data, and also without needing to coordinate for synchronized training. Is that clear? Cool. So this paradigm have two unique properties. The first is, as I just mentioned, it enables data contribution without sharing the data. And I think this is very important in practice because we all know data is highly valuable, and it's very difficult for data owners to publicly release the data because they know this is valuable. They want to remain having full control. So with this training algorithm, data owners retain having full control over the data, and they can still contribute to the single combined model. I think the other thing that is very important is that this supports easy data addition and removal without needing to retrain all the model. And this is possible because training is completely modular and independent from each other. For instance, if one of the data owners, say New York Times, want to opt out from this combined model, that what we need to do is just to remove expert or model parameters contributed by New York Times, and the rest of the model is guaranteed to not make use of New York Times data. And this is very useful because data opt-out can happen very frequently. And previously, there was no way to do this in a guaranteed manner. I think another thing that is equally important is data addition. Naturally, we will have increasing amount of data. Some data may come later, or we may discover some data owners have valuable data only after training is completed. If you have new data, what we need to do right now is to include it in the data pool and retrain the model either from scratch or from mid-training. But with this, we can just let that data owner to train their model and then contribute to the combined model. And this can be done without needing to do retraining from other data owners. Is this two features clear?
Yeah, I think there was a question in the chat,
okay.
Which is, can this framework basically be used to add like other modalities like into this model?
Yeah, that's a great question, and thanks for speaking the question. And yeah, that's a great question. So in this paper, we only did text only, but I do believe this can essentially be useful for multimodal models too, especially because these days we are now seeing increasing number of any-to-any models that has some sort of mixture of experts architecture. Well, this is a we'll talk about it later, but our architecture is basically mixture of experts. So if we can build a multimodal model with mixture of experts model where different experts are specialized for different modality, then it is possible. And I believe we are seeing increasing number of those kind of model. I think people call it mixture of transformers. I think there are some papers from FAIR, and also Python's bagel model is also in that category. So yes, I think theoretically we can apply that for multimodal setup.
I see. I also had another question, which is basically like, are there some kind of constraints or bounds on like the number of modality, or not modalities, number of data sources you can add like before it gets bloated? And then also like in a specific data source, like do you need there to be some like heuristic amount of data present? Or like, for example, like what if all of the data contributors were only contributing one data sample or something?
I see. Yes, these are all great questions. So for the first question about if we have constraint on how many experts or how many data sets to add. I think this is an empirical question. Theoretically, yes, it's not bounded, but empirically, I think there are a few challenges. The first is the router. So we'll talk about it actually later, but there's a router that has to decide which expert for every layer. And if you have more data owners, then that means your candidate is larger. So that means there is more likely to have some errors on that. So that's one issue. The other issue that I actually included as limitation at the end of the slide is right now, as you have more data owners, the model size gets very large very quickly. So even though you're not activating all experts, you have to load all these experts into your memory, and that can be a big bottleneck. In fact, this is also the not a limitation, but a downside that standard mixture of experts also have. When they have a large number of total parameters, even if you're not activating all, then you need a lot of memory. So I think there are some practical limitations that prevent it to scale so much, but I think this is issues that we can solve in the next generation of this model.
I see.
Yeah. I think you asked the second question. Sorry, could you remind? I think you mentioned about the data size.
Yes, like is there some requirements or something about that?
Yeah, that's also a great question. So in our work, we'll talk about this later, but one data owner is basically training one FFN, which is pretty big. So in this particular architecture, you need enough data to train one FFN. However, I think in the future, if you use a fine-grained mix of experts where each expert is small enough, then the required size of the data will be much smaller.
I see. There are two more questions, and then I think we should just move on after, just for time. So Matei asked a follow-up about the different modalities thing, which is like, basically, does the original model architecture have to support like all the different modalities from the beginning, or is this something that can be added on? So like, for example, if you trained a text-only model, like, can you add on other modalities, or does this have to kind of be baked in from the beginning?
Yeah, that's a great question. So I guess for this work, our motivation was that the data has to be completely distributed and there is no sharing. If we keep that constraint, I think the original model has to see some multimodal data, because otherwise the model has only seen text only, the model has only seen image only, and they have never seen them jointly. So I think that can be limited. However, if you say we don't necessarily worry about no sharing or no joint training at all, we just want training to be efficient by doing some sort of modular training, then I think it's okay for the starter model to be text only. In fact, I think the existing models like mixture of transformers or Bagel that has a few experts specialized for different modality, most of them start from the text-only model and then add vision model later. But they do some sort of joint training on multimodal data.
I see. And then the last question is, Raghav asks, basically, like, when you're training with this paradigm, do you observe some kind of training collapse or like big loss spikes, or is it relatively stable?
That's a great question. I think this is relatively stable, and that's an interesting question because it's not this work, but we also previously had a mixture of experts model that is standard mixture of experts, and we call it MoE. I'm not including in this presentation, but we did it last year, and for training a standard mixture of experts, we actually saw a lot of low spikes, and making training stable was extra important compared to the dense model. However, in this model, we're not actually training all mixture of experts jointly. It's either just dense model or a small mixture of experts with two experts. So because of that, I think training is more stable.
I see. Okay, I will let you move on.
Yeah. Thanks for any questions. And hopefully, as I go through the more details about the method, things are more clear. So yeah, I'll continue. Okay, so I talked about the problem setup, but now the question is what are the existing approaches or alternative approaches without using mixture of experts that can solve this problem. And in fact, this exact problem setup wasn't really studied previously, but there are some existing techniques that could be applied to our problem setup. So let's survey that. And one of them is model merging. There is a huge literature on model merging, where the key idea is you have a set of N models trained independently and then merge that into a single model to boost performance. So if we would like to apply model merging, then what we would do is, as I said, we start with a starter model, then each data owner take it and continue pre-train on their data. So in the end, we will have 4 models in total from this figure, and then we can apply model merging techniques over these 4 models. And model merging can be broadly categorized into 2 different approaches. One is called model soup or weight merging, where the idea is we do weighted weight merging over all parameters into a single model. And then the other is ensembling, which means you keep each individual model separately, but then when you have a test input, you get a output probability distribution from each model, and then do weighted ensembling over them. So both model soup and ensembling are actually standard practices in standard language model training for boosting model performance. So for instance, what people often do is they have a pre-trained model, and then for mid-training, they have a set of slightly different data mixtures, train on each of these data mixtures independently, and then do model soup. That is a pretty standard practice. However, one big difference from those setups and our setup is that in our setup, each data sets are completely disjointed from each other. They have very different distribution. Whereas previously, how people have been using is that they share similar distributions, although there is small difference. And in our experiment, we will show that later on, but we found that merging models trained on completely disjoint data sets is very hard, and they typically have some performance drop. This seems to be because when models are trained on completely different data sets, their weight space can diverge from each other so much so that it's very difficult to merge it back. So that's one option, model merging. The other option that I'm gonna describe is mixture of expert merging. So here we are using mixture of expert. So what is mixture of expert? I'm sure you just heard about it from organizers, but let me give you a brief recap. So this is a dense model that is not mixture of experts. I'm showing a standard transformer block that consists of some normalization layers, multi-attention, and then FFN. And normally FFN is the model that consists of most of the parameters. In mixture of experts, what we do is instead of having one giant FFN, we have a set of small FFNs. And we often call it expert or expert model. So in this figure, this has n number of FFNs. And then the key idea is we're keeping all n FFNs, but at inference time, we will activate only a subset of them. For instance, if we have in total 64 experts, we'll activate 8 of them. And then you will notice there is a thing called a router. This router can be seen as an n-way classifier that decides which 8 out of 64 experts to activate. And because this is quite important, just to zoom in, this router weight is basically a router matrix like this. So what happens is before this mixture of expert model, there is an input that is coming from the previous layer. It's basically an h-dimensional vector, and then we need a router matrix that is h by n matrix, where n is the number of experts. And then if you do matrix multiplication, your output will be n-dimensional vector. And then you can think of it as like each number here represent how likely each expert should be chosen. So once you have this output vector, what mixture of experts would do is to take argmax k, where you find the indexes with top k scores and then activate them, whereas the other ones are not activated. So we'll talk about this later. So I wanted to give a brief overview of how mixture of experts and the router works. So how do we use mixture of experts in our problem setup? So again, we have a starter model that is a regular dense model, only has one FFN, and then each data owner takes it, does continue pre-training on for training their own model. And then we merge it through mixture of experts. And what we do is first, we keep each FFN separately, so they're not going to be merged. So they serve as individual experts in mixture of experts. And then we have a few shared layers like normalization and multi-attention. For this, we do model soup or weight merging, which is just averaging parameters from different data owners. So that's how they make mixture of experts. So the nice part here is that architecture-wise, it's exactly identical to standard mixture of experts. So you can think of it as a different way of training a mixture of experts. But for inference or for serving, you can use existing serving infrastructure for serving standard mixture of experts, which is a great benefit. However, there is one limitation, which is it requires training on all data sets jointly after merging happens. So it's not that after merging, you can use the model as it is. You need to do some joint training over all data sets. And the main reason that we need that is because of this router. As I mentioned earlier, this router needs some parameters to train, which is the router matrix. But then when we merge different dense models trained independently, we don't really know how to form the router. So they typically need to train this router or all models, all parameters of the model on a union of all data sets. But as we discussed earlier, in our problem setup, the key restriction is that each data set should remain local. We can't really have a union of data set and train a model jointly. So this method as it is cannot be directly applicable to our problem setup. So now the key question we want to ask is, we do want to leverage the mixture of experts architecture because it has this nice modular properties, but can we remove the need for joint data access so that each data can remain completely local? Is that clear?
Yes, there was a question in the chat. Sorry, I have to keep going back and forth. So LZ asks, basically, does this setup in general, I guess option 1 or option 2, work better when the data is like the data sources are pre-clustered, and like is there some sense of like homogeneity or heterogeneous data that kind of affects performance, or like was this studied at all?
I see. That's a great question. So in our setup, we assume the data sets that are independent from each other is based on the sources. For instance, we consider all Reddit data as one data set and one PDF as one data set, things like that. But that's a great question. And there has been some prior work that take all the common crawl data, like public data, but then they clustered based on the domains. Using k-means clustering, and then apply a similar approach. Their model is not mixture of experts, but I think what you're describing seems very relevant. That paper is called Branch Train Merge, if you want to take a look. Yeah, so to go back to your question, I'm not sure if people have exactly compared making different data sets more distinct from each other versus not. That's an interesting question, and I can see the reasons for both. So yeah, the answer is we don't know.
I see. And then also like after for the limitation part, is the issue maybe like I'm not fully understanding this, but like if you were to do training on like the common crawl data afterwards instead of like training on the union of all of these like kind of more private data sets, like is the issue more about like the model that gets merged in the end is like not able to do anything, or is it just that it actually just can't perform these specific task?
Yeah, that's a that's a really great point. So like to repeat your question, basically the idea is after merging, you can still do training the all experts jointly, but using common crawl data because that's the public data. And we've tried that. That didn't work very well, and the main reason is because this blue one is trained from common crawl, then the router will be just biased toward just choosing blue one. It wouldn't really choose the other experts because they're out of distribution from the public data.
I see. That makes sense.
Cool. Yeah, I can go over our method and then take more questions.
Yeah.
Cool. So these are two approaches, and as I just mentioned, what we want to do is to keep mixture of experts architecture, but have a better training algorithm to remove the need for joint access of the data. So how do we do that? We came up with two different solutions to address this. The first one is called learning to coordinate, or I often call it mixture of experts aware training. The idea is once you have the starter model and then you are one of the data owner, you want to continue pre-train on that, then instead of doing normal continue pre-training, which should override all of these model parameters, you make it a mixture of experts with two experts. So you're duplicating FFN and then you're gonna add the router. So it's like mixture of experts, but just two experts. And then this blue one will be frozen. You're only training this second FFN during training. So it's equivalent to adding a second expert where this expert is initialized from the previous expert and then you're training on this. We'll talk about the router later on, so let's ignore that for now. And then after this training, the other data owners can do the same, and then we can merge it into a mixture of experts. So again, we can ignore the router, but this FFN is coming from the starter model, this FFN is coming from New York Times, and there are other FFNs that are coming from different data owners, and they can be merged. So why this is good? There are two reasons. First, because we are freezing the shared layers, we don't really have to do model soup, which has these issues of weight diverging from each other. So they are already synchronized. So that's one benefit. The other benefit is that this model is already trained to be mixture of experts. So when this drain FFN is being learned, they already know how to complement the public model that is already trained. So this can help the model to know that you need to coordinate with the other experts. And you're doing it with one expert only, which is the public model. But hopefully when you merge and you see other experts, they need to generalize. Is that clear? Okay, so we talk about FFN only, but we didn't talk about the router. So how do we solve the router problem? So as I mentioned, this router is basically, this router involves training a router matrix that is H by N, where H is a hidden dimension and N is the number of experts. So in this figure, N is basically 4. And what we're gonna do is we can actually decompose this matrix into n number of h-dimensional vectors like this. So if we look at the final model, then this router can be decomposed into 4 vectors where each vector is h-dimensional. And then each vector will correspond to each expert. So we have a blue router vector that is corresponding to this blue FFN. We have green one that corresponds to green FFN, and so on. I'll just call it a router embedding from now. And then once you decompose it, then what that means is each router embedding can be trained by each data owner separately. So when New York Times train their own experts, they need to train a router, and that's again a two-way classifier with 2 by h dimensional matrix. But in fact, this can be seen as 2 vectors, where one vector is responsible for the public expert, and then the other vector is responsible for the new expert we are adding. And then when we train the model, this public vector will remain frozen, while we are only training this R1, the new router embedding. So just to summarize, when you are training your own expert, you will freeze all the blue part and train green part only, which is one FFN and one router embedding per layer. And then once you do that, then they can be merged into a single mixture of experts. For FFN, they will just keep separate, just like standard mixture of experts. For the router embeddings, they can be concatenated to make it a single matrix. And again, because this RPOP is frozen, these are already synchronized, and then the R1, R2, and R3 can come from different data owners. Is that clear? Yeah.
Yeah, I think there was a. Oh, sorry. I guess the question in the chat, they answered it themselves. I was actually wondering one thing though, which is like so if the public router is fixed, like it's fixed across all of, like, for all the different private domains you fix it, right?
Yeah, RPOP is fixed.
I see. And so then when you train the new routers, or like for the specific data sets, is there like some kind of potential bias going on here? I'm not sure. Like, I guess that maybe the confusing part is the public router gets used at the very end, like when all of kind of the domains are combined. But the way that you train it, it's only with respect to one other router. But does this make sense? I don't know if it's like the way you normalize them is different in the individual setting versus in the full setting, because it's with respect to more experts in the full setting.
Yes, that's a great question. So first, one thing I want to clarify, I think you already know that, but like just in case it wasn't clear, even if you're training the green part only and the remaining part kept frozen, we are still using them during training. So during training, the data can be routed into blue part. It's just that they're not frozen. So I think in the end, it's not like only the green one will be chosen. We actually found they're pretty balanced. And I think we also use the load balancing to make sure it's not just the green one that is being chosen. But I do agree that the problem you mentioned is valid, because we're only training a model to choose from 2 candidates. And then at inference time, you suddenly have so many candidates. So this model can be confused. I think that happens a lot. And actually, when we did analysis, the error cases mainly came from suboptimal router decision. If router was perfect, then the performance can be much better, but the router was still, they were not optimal. I wanted to mention this in some of the open problem section later on, but one way to deal with this issue is to make the starter model to be also a mixture of experts, and in particular fine-grained mixture of experts, so that they already have router. And then when you add a new expert, then now it's not just 2 experts you need to choose from. It's probably n+1 expert, where n is the number of original experts. So if you can see more experts and more router embeddings during this independent training, then I think the generalization issue that you mentioned can be much better.
I see. And then someone asked a question. They said, I'm confused how the RPub is generated to begin with.
Oh, yeah. Sorry, that's one thing that I should have mentioned but skipped. We initialized these router embeddings from domain embeddings. So we already have the data. We use some encoder to map each data point into an h-dimensional vector, and then we average them to create the domain embedding. And then for RPub, we use it as it is because we're not doing any training. For other router embeddings, R1, R2, and R3, we use these domain embeddings to initialize the vectors, but then we can further train on them.
Yeah. Okay. I'll let you continue.
Yeah. Cool. Yeah. So these are 2 ingredients, and just to summarize the big picture, this is how FlexOlmo works. So we start with a model that is trained on public data only. So this is shared across everyone. And then each data owner take it and then do some modular training locally on their data. And in particular, what they do is to make it a mixture of experts model with 2 experts by duplicating FFN and then initializing the router from domain embeddings that I just mentioned. And then they keep the half of the model frozen so that they're still public model. And then the expert models, which are 1 FFN and 1 router embedding for every layer, they are trainable. So each data owner can do this training completely independently. And then once everyone is done with their training, then they will be merged into a single mixture of expert model. And in particular, the shared layers like multi-attention can be just brought by the public model. And then each FFN will be kept as separate experts. And then for the router, we do it by concatenating all the router embeddings into a single matrix so that it can be a single n-way classifier. So that's how FlexOlmo works. And as I mentioned, if new data owners come in, then we can incorporate them by adding their expert models to this architecture. If one of the data owner want to opt out later on, then we can do this by removing the expert models contributed by that expert. So for instance, if New York Times want to opt out, then New York Times contributed this green part of the model, so we can simply remove the green part. And the rest of the model is guaranteed not to use any New York Times data. Cool, so that's a summary of the method, and I'll now move on to our experiment. Before talking about the result, I'll describe the setup first. So the first thing we had to do is to define the data set for our experiment. In particular, we need a public data set as well as a set of private data sets. So for public data, we use common crawl, and then for private data sets, we use a set of domain-specific data sets, including math, code, creative writing, papers, news, Reddit, and educational text. One thing we try to be intentional is that some of these data sets are actual proprietary data sets where data owners have some restrictions. For instance, a lot of news data, these are actually extracted from Common Crawl that was downloaded a few years ago, but it has been known from a few papers that a lot of news providers are now applying the paywall restriction so that Common Crawl cannot have that. And then Reddit also have similar restrictions. We downloaded this Reddit a few years ago when there was no restriction, so it was completely fine for us to use this data. But now people cannot download the Reddit dump because Reddit now have some restrictions that we cannot download the data for model training. So these are semi-realistic scenarios that we try to incorporate. And then for other data sets in the first row, they are simulated proprietary data sets, meaning that they're actually public. You can download it today and then they're completely fine. But they are realistic domains, meaning that we chose the domains that gathering high quality public data sets are known to be very challenging. For instance, the math and code. And then these are the training setups. I'll not go over all the details here, but just to highlight a few points, we did experiments on 7 billion scale, meaning each expert has 7 billion parameters. So when we merge a mixture of experts, I think in total they have about 50 billion parameters. And then we copied the typical model config from the mixture of experts. For training, we pre-trained on the public data for 1 trillion tokens to have a public model that can be shared by everyone. And then after that, we assume that each data owner does continue pre-training on each of their private silo data set for 50 billion tokens. Okay, so now I'll talk about the result. In the paper, we included many data sets, I think about 50 different data sets. But for this presentation, I just brought some of the representative data sets as well as the average number. And in particular, MMLU Pro and AGI Eval are some of the general purpose benchmarks that are widely used. And then Math 2 dataset is actually the average of 2 math datasets, GSMK and Math 500. First, we show the result of the public model. This is a model that is shared across everyone, trained on public data only, and these are the results. Next, we compare with specialized experts, and what that means is the model that is fine-tuned from the public model, trained on each individual dataset only. And in particular, I show 3 of them here. So what we found is that continual pre-training on some specialized data helps in domain tasks. For instance, in math dataset, we see that the math experts is getting very good performance, which is not very surprising. However, we also found that it can hurt out-of-domain datasets. For instance, for MMLU Pro, all experts are getting worse results than the public model because they are only good at their specialized domain, but it's not good overall. Next, we compare with prior model merging method that I briefly described as option 1 and option 2 in the earlier presentation earlier. In particular, we have model soup, which is averaging all parameters into one model. We have BTM, it's a short name for branch train merge that is using ensembling. And then we have BTX that is using mixture of expert model, but requires joint training after merging. So we actually did the thing where we do joint training on public data because we cannot have joint access over all private data sets. So if we look at the result, we find that overall they do help. If we look at MMLF Pro and AGI eval, they do help over the training on public data only. So they're effective. However, they're not very competitive, especially when it comes to specialized experts. For instance, if you look at the numbers on math datasets, then all model merging methods are much worse than specialized experts like math experts. And we did some analysis on this and find that this is exactly the issue that we discussed earlier on model weights diverging from each other too much. So when we have math experts, code experts, and other experts, individual of them can be good on their in-domain data, but when they merge, then they do have some collapse issues so that they lose the ability they learned from specialized training. Yeah, and then finally we have our model, which is called FlexOlmo, and we found this is better than all the prior model merging method. It achieved 41% relative gain over previous public model. In particular, for the general purpose data sets like MMLU Pro and AGI eval, they are better than prior merging method as well as specialized experts. And then for specialized domain like math, it is getting very close or outperforms the specialized experts like math experts. So when we do averaging over all data sets, they're significantly better than all the other baselines. Cool. The last result that I wanted to present, which was personally more exciting, is that we also compare with unrestricted mixture of experts. This is a mixture of experts that is upcycled from the public model, but then is trained jointly end-to-end over a union of all data sets. So we can think of it as an upper bound model. And so this model is obviously better than all the models because it doesn't have this restriction of keeping every dataset private. But also, FlexOlmo retains 90% of the benefit of fully unrestricted training. I thought it's pretty exciting because that means if you're willing to pay for 10% of the performance gains, then you can have lots of exciting benefits, such as modular training, keeping each of your data private, and also being able to opt out later on or add new data sets afterward. Any questions on the result?
Yeah, I had 2 questions. Okay, so the first question was from a bit back when you talked about the opt-out. And so opt-out is a nice feature to have, but it requires us to keep the training completely paralyzed. Like what I mean is like if we think about it like kind of like a GitHub model where like so we have the base model first, everyone like forks off, they train it on their specific data set, and then we consolidate it at the end. And this allows for opting out to be easy because everyone's data is kind of kept something that's removable. Like you can remove the FFN, you can remove it from the merged the like normalizations and I mean the attention layers. But anytime we think about, oh, what if then, after we have this ensemble, someone takes this ensemble, continually trains it with, like retrains all the parameters on a new data set, right? So it's like it seems like the opt-out feature kind of imposes this constraint of keeping training completely paralyzed and like doesn't allow us to like sequentially also train the model. So that's something I was just thinking about when you just mentioned that. It's like, how do you think about that?
Yeah, I think that's a great point. Like, for instance, if you already release the model wedge publicly, like on Hugging Face, so that people can download and fine tune, and then some people download it and fine tune on them, then you already have dependencies to that data. And then if you opt out, then you can probably remove that model from the model that is uploaded on Hugging Face. But there are still models that are fine tuned and downloaded. So we're not entirely opting out in that sense. Is that right? Like, is it what you're asking?
Yeah, I guess like it's hard to do like a real like complete opt out once we want, because like from a practical point of view, it seems like at least like correct me if I'm wrong, but the visions, it seems like very similar to like a Git for models, right?
Yeah,
Like
yeah.
people can fork, train, contribute.
Yes.
But anytime we have like the sequential nature where someone uses someone else's, like use a previous version of the model that had prior data, and someone trains, and the new checkpoint now is like using like has all this like dependencies. It's hard to like try to remove this dependency out.
Yes,
Right?
yes, that's a great question. I think you're right that if you publicly release the model and then someone else took it and then fine tune on it, you have dependency. And then if you opt out, you can opt out the specific checkpoint, but models that came after that
Yeah.
as additional artifact um, um, wouldn't be have complete opt out. I think that's right. My understanding is in practice, still being able to opt out the original checkpoint is a big deal because currently we even cannot do that. And I think this is the same when you upload a data that is a collection of data sets, and when you want to opt out a subset of them later on, then people will then the party that uploaded this data can remove the problematic data so that the upload version will be clean. But if someone downloaded that data already and then train a model on that, then that artifact is not in their control, so there's nothing we can do with that. But I think that is already a big benefit that you can remove that from the public version. I think another thing that we can do is if the data is so sensitive and we want complete opt-out, then maybe that model has to be served through API access rather than releasing the model weight, so that you cannot really so that you can have control on which model checkpoints have dependencies, so that maybe you can retrain them.
Yeah,
Yeah.
that makes sense. Yeah, it's very interesting to think about how to kind of like fully scale this to the public. The the last question I was thinking about is when you talked about the unrestricted MoE. So uh have you noticed there being like evaluations that are utilizing like multiple different experts? Um um Actually, yeah, wait. So stepping back, what is like the top K value for FlexOlmo? Like, are you averaging in this evaluation, are you averaging multiple expert outputs?
So we have in total 8 experts, and we are activating 4 out of 8.
Oh, okay. Got it. And do you notice like um between the routing
It's
the
very
routing in the unrestricted case and the FlexOlmo case, are they like similar, or is in the FlexOlmo case is it more sparse and the unrestricted more uniform?
Mhm.
Yeah, how much mixing?
Oh, that's a really great question. We haven't actually compared FlexOlmo and unrestricted MoE in router behavior, so we haven't done that. One thing though is one thing I thought that might happen in FlexOlmo is maybe for every layer they always choose the same experts. Like if we are evaluating on math data, maybe they will always choose math experts, but surprisingly that wasn't the case. So when we look at every layer, they may activate slightly different sets of experts. So I think we are making use of the MoE architecture in that sense, because you don't have to be restricted by just using one expert or two same experts.
Got it. Okay, thank you. Yeah, that's very useful.
Yeah.
Oh yeah, there are like a few questions from the chat. I guess we can go through them quickly.
Yeah, because actually I'm almost done. I only have a summary slide.
Oh,
and
actually, yeah. Then go for it, and we can end.
Finish, and we can
Yeah.
get questions afterward. Yeah, cool. So that was the result. I wanted to mention one more analysis really quick, which is opt-out experiment. So I mentioned earlier that you can opt out one expert to remove the impact of the opted out data, while the remaining models can remain unaffected. So we try to see if that's actually the case. So we have 8 expert model that is original FlexOlmo, and then we opted out news experts trained on news data, so that we now have 7 experts. And then we try to see how much impact there is in a few downstream tasks. And what we found is that for news generation task, which is definitely relevant to news, there is a performance drop, which is expected. However, for other downstream tasks that are not relevant to news, then opting out news experts have minimal impact. In fact, in some cases, it can even improve, likely because router now have fewer candidates to choose from. So this is a demonstration that shows that opting out experts have minimal impact to other experts. Cool. So I guess that's almost all. I just have 2 slides for summary. So just to summarize, we learned previously that standard mixture of experts has this nice modular architecture, mainly for improving efficiency in training and inference. But I argue we can also use it to enable training on distributed data sets where different experts can be trained by different parties without needing to share their raw data or even needing to have a synchronized training over all model with data owners. And then once these experts are trained independently, then they can be merged into a single model. I mentioned a few challenges, but I mentioned the way we address them is MoE-aware independent training, where each model is trained using the public models as an anchor model so that they know how to coordinate, as well as the non-parametric router, where we decompose the router into a few vectors that can be trained independently. And then we also show some result where we show our model can significantly outperform training on public data only because it's making use of these additional data sets that we could have not been able to use. We are also approaching joint training on all data sets, which was unrestricted MoE. I didn't mention so much earlier, but it actually also significantly improved training efficiency because each expert training is now modular. So you don't need to do joint training over all mixture of experts, which is typically very expensive. And also it provides free opting out for data owners, as well as easy addition if you want to add new data. I also wanted to mention a few limitations of our current FlexOlmo, as well as some open problems. One is, can we make use of fine-grained mixture of experts to enable fine-grained data addition? There are 2 reasons I think this is very important, and I think this is related to some earlier questions we had. One is we want to scale the number of data sets that we can incorporate. Right now, every time you have a new data owner, you have to duplicate the original public model. So the model size can go very large very quickly. But if you use fine-grained mixture of experts, this can be mitigated. The other reason I think is important, also related to earlier question, is right now we assume each data owner have at least 50 billion tokens, which could be quite a lot. And the main reason we need this is each expert is pretty big. If we can use fine-grained mixture of experts, each expert model can be much smaller, and data owners who have data with modest size can also participate. As I mentioned, scaling the number of experts / data sets is very important. I think another thing that I'm very excited about, and I'm kind of hinted, but we didn't necessarily demonstrate it in the experiment, is can we leverage this architecture and training method to allow continual learning, where you start with some model that is not good yet, but you gradually add better data sets over time so that in the end you can have much better model. I think this can be very useful and exciting to develop a model that is continuously improving. Finally, this is a more technical problem, but how to train a better non-parametric router is a big issue. As I mentioned earlier briefly, we found that still a lot of error cases come from suboptimal router decision. The main reason is because the router was trained to choose from 2 experts, but an inference time that has to generalize to many experts. So how can we have a better training method that can improve this generalization aspect can be an interesting open technical challenge. Yeah, I guess that's all, and thanks for listening and staying with me here. And I can take more questions now.
Yeah, thanks for the very nice presentation. Actually, I actually have I'll say 2 questions that's slightly different from the technical content of the talk. So one, you can easily imagine sort of the application that just have algorithm or method can be sort of have like sort of quote unquote like online platform of where people can contribute data, and you can have different routers to different experts. But interesting to applicate sort of to implication of this, which is something quite interesting to think about, which is I think there's some early work coming out of Stanford where you basically are able to sort of quote unquote evaluate the price or the valuation of a data points. Imagine, say, in the case of New York Times providing data. I don't know if you ever thought about how to quote unquote evaluate how much value the data that New York Times provides provide actual value to the quality. So that's the first question. So the second question is, which is sort of interesting question in terms of sort of game theory, sort of an incentive question, which is imagine you have an open platform, but there's quite questions. How would you able to sort of incentivize people to provide the data? You pay them a specific price, or on the other hand, is there a way to prevent people provide quote unquote malicious data? So if I'm like someone who wants to attack the model, I can somehow provide data that are malicious, right? Just intend to be bad in some definitions of bad, and then somehow have the model trained to do some bad things. So how have you thought about how to prevent such malicious use cases and or quote unquote incentivize better behaviors?
Yeah, these are all really great questions. Thanks for asking them. I think these are very, very important for like practically applying this for actual like platform, as you mentioned. These are really great questions. Thanks for asking. So to answer your first question about data value, yes, I think eventually this would be really great if we have a way to evaluate the value of the data and use that to motivate data owners to contribute or be able to compensate them. I don't really have ideas for what specific method we can use to evaluate the data, but I think in practice, any data evaluation method can be applied here. Actually, one application that we were thinking is this can even be like one pathway for like data negotiation, where if like for B2B application, for instance, if you want to use someone else's data, you will have to purchase the data, and then now that data will be transferred to you. That's one way you can like have a data collaboration or data collaboration. But this can be a new way of doing data collaboration where you are not purchasing the raw data, but you are purchasing the expert trained on their data. And this can be a way to incorporate their expert model into a single model. And if you are thinking about application like that, then as you mentioned, being able to evaluate the value of the data will be very important. So I'm not super familiar with the individual method, how to do that, but I do think that will be a really practical, that will be very practical to use. I guess the second question was about how to prevent like unsafe or harmful experts. I think that's also a really great question because, yeah, if we imagine we have an open platform and everyone can contribute, then there could be harmful experts, like, and then we need a way to monitor that. For that also, I'm not very familiar with specific individual method to identify them, but I think we can easily use any existing method to identify harmful experts and be able to opt out. There's one additional benefit, which is these also provide a natural way to do attribution, meaning if you have a set of experts, and then you see the router decision, then you see what exact expert is contributing for a model prediction by seeing how much it affects the router decision. So so to summarize, I think any monitoring algorithm can be used jointly with our method, but this can be even easier to monitor because you know exactly which expert is contributing to some harmful prediction, and those experts are likely to be the problematic expert.
Yeah. Thanks for the answer. This is great. I think it's a very interesting, easier to think about very interesting and cool applications that we can build upon on top of this.
Thanks. Any questions? More questions, either from chat or from organizers?
I think Alex will have a couple questions.
Yeah, there's some from the chat. So Raghav asks, basically GPT-OSS and Gemma 3 were trained for a lot longer. So post-training is kind of harder. But so for FlexOlmo, he asks, what are the trade-offs when training for more epochs, given that we have limited compute?
Yeah, great question. Yeah, so we couldn't like train as long as like other like GPT-OSS or Gemini models, mainly because we pre-trained ourselves and we had limited compute. But I am not. Well, I think this is a great empirical question. Right now, I cannot think of any reasons that some of the findings we have may change depending on like how long we train the model. I think maybe the public model will be much better because it's trained way longer. But I think we all know that still adding some specialized data is helpful on top of that. So, so yeah, my guess right now is that a lot of findings can be applied even regardless of how long the model was trained. But I think this is an empirical question.
Perfect. Sorry, I guess there's a lot of LZ asks, are you able to extend to post-training while retaining this whole expert isolation setup?
Yeah, that's a great question. So yeah, so to clarify, our model is all like pre-training or mid-training. There's no post-training, but I think in the end we want to post-train. So how to do that is important. I think there could be two different answers to that. One is we take this FlexOlmo as like its standard mixture of experts, and then we just post-train on it, just like we would do post-training on the standard mixture of experts. And then I think one problem is then we are kind of like mixing the impact of different experts. So for instance, if you opt out one data, then now you have to redo post-training because you can't simply remove one expert and hope that the rest of the model hasn't seen the impact of that. So there are limits. However, in some sense, post-training is significantly cheaper than pre-training. So I think that might be fine in practice. So that's one answer. The other reason is we might be able to extend it from post-training. For instance, maybe the public model that we start from can be post-trained model instead of pre-trained model, and then we can add other experts that are either pre-trained or post-trained, and hopefully they can generalize. I'm not really sure if that would be possible. I think it might be possible that it generalized. There's also the other possibility that generalizing across pre-trained model and post-trained model have additional challenge. I think that's an open problem.
And then I guess the last question is, do you think that model soups could perform similar to your setup if they weighted their contributing models better?
Great question. So we also tried that. So when we tried model soup, we tried two versions. One is uniform model soup, which is actually what most people do. And the second is some sort of weighted model soup where we have different weights for every input. And we found some mixed result. Sometimes it was better, especially when you have the right weight, as you mentioned. But we also finding the right weight is actually very difficult. Yeah, it's possible that what we did is pretty preliminary. We followed the setup from branch tree merge on finding the weights, where we use like some sort of domain prior. There might be more advanced method to find the better weights. We haven't fully explored that, but I think that could be an interesting open problem. I know it's a practical question that a lot of people are excited about.
I see. Yeah, I think that should be it from the chat. So thank you so much, everyone, for coming. Tomorrow we will be back focusing on attention sync stuff, but that should be it for today. And yeah, thank you.
Yeah, thank you for having me.
Thanks, Sewon, for talk.
Thank you. Bye.
Bye.
Okay.